moment in Jenga, where you're slowly sliding out a block, hoping everything doesn't come crashing down. Now imagine doing that, not with a tower, but with a photo. This is visual Jenga. It's a new way to test how well a computer really understands a scene by removing one object at a time from an image and seeing if everything still makes sense. And the trick, counterfactual inpainting. Basically, the model asks, hey, what would this picture look like if this thing wasn't here? Then it checks how well it can fill in the blank. If it's easy to replace, like a cat on a table, the cat goes first. If the scene falls apart without it, like the table, it stays. No physics, no training, just smart inpainting and object reasoning. Let's pull the first block and see what happens.
Let's start with the big idea. Is it enough for a computer to simply recognize objects in a scene? The authors argue that it's not. Recognizing objects is one thing, but truly understanding how those objects relate to each other is a different challenge. This paper introduces a task they call visual Jenga, inspired by the game where removing the wrong block topples the entire tower. The analogy works like this. Imagine removing an object from a scene. If you take out something crucial, the scene might look strange or physically unstable, just like knocking out the wrong Jenga blocks. However, if you remove something less critical, the scene remains well-formed. To figure out what's removable, they use a pre-trained inpainting model. If you remove an object and inpaint the hole it leaves behind, the quality of that inpainted result indicates how important the original object was. If the inpainted version looks perfectly natural, maybe that object wasn't very important to begin with. Look at the figure shown here of a stack of bowls. Each bowl disappears in sequence, yet the stack remains visually coherent. This example sets the stage for the entire paper. The goal is a new kind of scene understanding, one that focuses on dependencies and how objects support or rely on each other. That's the essence of visual Jenga. Here we delve into how the system decides which object is more crucial. The key method is called counterfactual inpainting. Remove each object in turn, then let a generative model fill in the gap. The variability of those inpainted results signals how dependent the object is. If removing the cat from a scene leads to many wildly different inpainted outcomes, maybe a plant appears or some random item, then the cat is considered flexible. By contrast, removing the table might consistently yield another flat surface. That stability suggests the table is more central. They quantify this by measuring the similarity between the inpainted results and the original image, using embeddings from contrastive language image pre-training, CLIP, and self-distillation with no labels, DINO. If inpaintings are all over the place, the object is flexible. If they're similar to each other, the object is a structural anchor. This indicates who depends on whom in a scene, guiding which object should be removed first in visual Jenga. They also connect this to a historical context. Early computer vision in the 1960s aimed to interpret 3D configurations and reason about physical space. This paper extends those classic efforts by using modern generative models, linking back to a long-standing quest to move beyond simple object detection. Next, the authors remind us that scene understanding is more nuanced than just labeling objects. It's about how objects depend on one another. Picture a cup on a table. The cup needs the table for support, but the table doesn't necessarily need the cup. Try searching images for cup, and you'll often see it resting on a table. But searching table doesn't guarantee you'll see a cup. This asymmetry matters. Check out the Venn diagram shown here. It visually illustrates this idea. Cups overlap with tables, but tables stand on their own. That's the groundwork for defining object dependencies. From there, the paper sets up the visual Jenga task. Remove objects from a single image, one by one, in an order that keeps the scene coherent. The twist is that they're not doing this with manual rules or human labels. Instead, they use big, pre-trained models that learn from large-scale data, letting object co-occurrences in images drive the process. They formalize dependency with conditional probabilities. If seeing object A makes object B more likely than the other way around, then A depends on B. This approach sidesteps traditional causal structures. Instead, it leverages visual patterns from large-scale data, capturing real-world object usage from everyday photos. Now let's see how the pipeline works in practice. First, a model called MOLMO places points on each object it detects in the image. These points act as reference markers. Then they use the Segment Anything model, or SAM, from Meta to transform those points into segmentation masks. That gives you precise outlines for every object in the scene. Once the objects are segmented, the system goes into counterfactual mode. It masks out one object and uses a generative model to inpaint multiple times, creating different what-if versions. Then it measures how much these versions differ. If they're highly varied, that object is flexible. If they're nearly the same, that object is structurally important. This diversity gets computed via comparisons in clip and dino embedding spaces. The object with the highest diversity score is removed first, because the scene can live without it most easily. Then everything repeats for the next object. Check out how they justify this strategy. Rather than rely on raw likelihood scores from diffusion models, which can be noisy, they use inpainting diversity as a proxy. It's a simple but effective way to measure how objects anchor a scene. This modular design cleverly reuses existing models, Molmo, SAM, Clip, Dino, and Adobe Firefly for final inpainting, without retraining them from scratch. Let's look at some results. You'll see several rows of images that illustrate how the method performs. Notice in the first row, there's a neatly stacked set of 4 tires. The system removes them top to bottom, just like a human might. No drama there. In another example, there's a cat sitting on a laptop, which is on a table. The method removes the cat first, then the laptop, and finally the table. Makes sense, right? You wouldn't remove the table from under a laptop and cats. Similarly, a cup resting on a saucer, which is on a table, disappears in the order you'd logically expect. Cup first, saucer next, then table. Another fun illustration shows food on a dinner plate. The system wipes out the soup and sauce before removing the plate itself. And it even waits on the spoon until the right moment. There's also an example with glasses perched on a stack of books. It doesn't remove the glasses until the books underneath are gone. Each illustration, marked by yellow arrows, demonstrates how the approach respects the relationships between objects. It's not random erasure. It's deliberate, step-by-step removal that mirrors the real-world dependencies you'd see in everyday situations. Check out Figure 6 for a scene with a busy breakfast table on a balcony. Notice how the system carefully removes items in a sequence that keeps the overall image looking natural. Objects hidden behind others come into play only when they become fully visible. It's neat how the method adapts as each new view of the scene emerges. In Figure 7, there's a picnic table, a wall, and some bicycles. The system gradually clears smaller table items, then deals with the table, and eventually tackles the stone wall in the background. It even removes the bikes before the wall, since they appear to lean against it. Now look at Table 1. It provides a quantitative comparison on the NYUV2 dataset and the hardparse dataset. You'll see the model achieves over 91% accuracy in pairwise object comparisons on NYUV2 and outperforms standard baselines on hardparse. When it comes to removing all objects in a scene in a way that remains plausible, it achieves a success rate of 71%, beating simpler heuristics by a wide margin. The takeaway? Size alone doesn't define importance, it's the dependency relationships that matter. Continuing the comparison, look at Figure 8. You'll see 4 rows of different removal strategies for a living room. Front to back, small to large, and top to bottom heuristics each fail in their own way. Like removing a table before the cup on it. That's obviously incorrect if you think about physical support. In contrast, the 4th row, which uses the author's method, removes the cup first, then the newspaper, tray, rug, and eventually the sofa. That sequence simply makes more sense. Now turn to Table 2, where they do an ablation study on the diversity score. They compare using only Clip, only Dino, or both together. The results show that combining Clip and Dino gives a solid performance boost, especially on the harder scenes in hardparse. Accuracy on NYUV2 jumps to 91%, and on hardparse, it climbs to 65%, beating single embedding methods. They also point out why heuristics struggle. Even the best heuristics manage only 43% full scene success, and front-to-back collapses to a mere 9%. Text-based solutions with large vision language models don't do as well when asked to visually remove objects. They can describe the action in words, but actually executing it in a realistic image is a different story. That's where this inpainting-based approach stands out. Finally, here's a peek at a complete office being cleared out, object by object. It's surprisingly thorough, tackling not just obvious elements like desks and chairs, but also smaller items tucked away in corners or behind furniture. The scene remains visually consistent after each removal, which makes the entire process satisfying to watch. But no system is perfect. Figure 10 illustrates 3 common failure modes. First, there's an issue with Adobe Firefly. the generative model used for inpainting. If there's tricky lighting or strong shadows, Firefly might mistakenly reinsert the object. Second, if Molmo fails to detect an object, like overlooking one of several glasses, it never gets considered for removal. Third, SAM can sometimes pick only part of an object, like a monitor screen without its base, leading to partial removals. These failures remind us that the pipeline depends on each detection tool's accuracy. Still, the overall performance is impressive. By modeling which objects depend on others and removing them in the right order, the method achieves a new kind of scene understanding, one rooted in real, observable dependencies. Thanks for joining us today. Happy exploring!